Maybe I will first talk about some like over overall view in our approach in this problem. We are trying to study study like blockchain economics issues. The main issue here, I think, is like in a traditional in a traditional approach in economics, the main focus are like in a one shot, like incentive analysis. So when things go to continuous time, like the technique in economics are not really we don't have very much like good economic techniques. However, and sometimes we don't worry, but with blockchain, life becomes simple, but more issues came up. So it's like when we have when we have like a blockchain like Bitcoin in the beginning, we have this like we have those things called majority vote when things are not decidable. So in the first like one shot analysis is good, but then there's this work by I don't know how I said his name right. Ear or not from Cornell. Like they have this paper in majority is not enough. So there they have like a equilibrium attack to the majority rule. So people can have like a minority can still like get more block award in the end in compare to their fraction of computing power. So so in this we try to look into other direction to try to understand this in this real economy in say in blockchain when we have like a very few parameters, we understand a lot of things because they are algorithmic designed. So bounded rationality from Simons doesn't work that much. So so this in this work we try to look at like the old traditional approach, say reputation. So in economy, many things like people don't do bad things because they want to keep their good reputation. So we try to look at blockchain as an example. So here we focus on permissioned blockchain because reputation is. I think we can still keep a reputation on people with their IDs, but for permissioned blockchain, we can do analysis much more easy, like probably. So this is one of the like one approach we think is it makes some like make some different view on the economy build on the blockchain. So but yeah, so maybe we'll just get started. So this is like we focus on this transaction verification. Actually, this is not it's not everything we can do use this technique, but it's one thing we can try. So, for example, in blockchain, this is one thing like people have worried about because there's no incentive for people to do like reputation to do verification if this like block is formed correctly and did somebody do some tricks there, did they follow right design the protocol, design the algorithm to do everything. So so when we have like when we have a lot of transactions, the good thing is like if one person is good, then other people don't need to do that verification. So we try to reduce the number of verifications, say in blockchain design. This is the idea. Like we try to see if some people with good reputation, he passed over a block, we may think, say, this block is good. So here is the idea. So we reduce the cost of verifying a transaction. Now, actually, it's not just verifying. It's not verifying wrong transaction. Of course, if it's wrong, we need to check it, right? Because we are not sure it's wrong or not. So sometimes we don't check to save the like the cost. So we want to figure out whether they are good or bad with high reliability. So here is like when we have permissionless and permissioned blockchain. So we can, when we have permissioned blockchain, so it's easy to tie the trustfulness through the task they finish. So to watch for the long-term behavior. So for permissionless, we can still do that, but it's maybe everybody disappear, and so everyone coming in becomes new, then reputation doesn't make sense anymore. So we still need some long-term, non-lifetime for every miners in the permissionless blockchain to make things of some sense out of it. So this is like this becomes things become easy this way, right? So we can basically do some we just count so we can just count whether they are good, they did something right or did something wrong later. So decide the reputation. Then we need to design an algorithm to use their reputation. So first of all, we consider a simple model. So this model, we have providers, miners on the left side, connectors connect this transaction, put them in blocks. Then governors, like we just call them this way, but governors just validate those transactions connected. Just I cannot see what's below, so I move through this a little bit.
If you move your mouse to the left, okay.
Yeah. Okay, now I think it's okay. Yeah. So this is the picture we use here. So we use some notations. Provider is P1 to PL. Collectors are C1 to CN. Governors from G1 to GM. Then every provider connected to UI collectors, and enabled transactions are written as TX. Then if it's labeled, we have TX and label. And then labeled transactions are followed by the signature to make sure it's done by this person. So label is just a label collected from the collectors. So the blockchain block structure, we have sorry, it's here. So we have a serial number, then we have a leader in the governors and the transaction list up there. And MT is like we put a tree root there, and H is a hash value of previous block. B will be the number of valid transaction in a block. Then we have an upper bound on total number of transactions in a block called the B limit. So the idea is like we design this reputation list there, and it's so P is number of, let me just go back to here. P is number of the providers of the transactions. Then each of them has a reputation. So it's RI is like their reputations. Connectors linked to PI are written as CI until CU of I. So each of the connector, each of the provider will give will have a rank. So this will be used the probability collected selected by a governor to compute the use softmax function, which is proportional to that reputation. So here is the steps. So in the connection phase, provider just offer just a moment. Sorry, just one moment. I'll move it a bit. So provider will send the transactions and to connectors, and then broadcast. So they are broadcasted to the connectors, connect to those providers. Right. What happened? Oh, I see. Okay. So then connector will validate those transactions and submit them to the governors in the second phase. It is processing. So in the third phase, it's processing. Then we do transaction screening, and we update the reputation, and we decide on the consensus on the final result. Then we propose this next new block. So this done by the governor, the leader in the governors, I think. Yeah. So here is a standard probability analysis. It's like using a softmax function, and so everyone's reputation is raised to the power of e to the power of eta times ri, the reputation, and so this will be the fraction in the probability it is selected. Then once CIK is chosen according to the probability, then the leader will not check it if its neighbor is. This is so when CI is -1, then we put it into unchecked list. Then if it's a positive one, then the checks update it, and if transaction X validation is valid, then we add it to transaction list. Otherwise, we put it in the invalid list. So next we connect we update the reputation of the providers. So we add, if it's a positive label, the connector gives the positive label, then its reputation is increased by 1. If it gives the wrong label, then the reputation is reduced by 1. The reputation is used in choosing which one would let me just go would be used to choose by collectors to we decide on the collector to choose to decide on if his reputation is high, then there's a good probability its result is correct. So next, the leader will be selected by the governors. From the governors. So at each end of the round, the leader will propose the block and to construct the invalid list and unchecked list in the Merkle tree. So the provider then figure out his validated transaction and are checked or not, then decide whether to send them again. So
may I answer a question?
Yeah.
Why the list of invalid transactions and the list of unchecked transactions needs to be kept? I mean, the Merkle tree, the Merkle root needs to be kept for the invalid transactions and unchecked transactions. Is that to be used in some future rounds?
It's used, yeah, it's using the by the provider part. So his valid transaction are, let me see, yeah.
So are you actually keeping a trace mark of the invalid ones? So the block only contains the valid transactions, right? But you're saying that you are putting some invalid transaction list and keeping the root of that Merkle tree.
It's easy to check them because they're like so.
So that if a transaction enters the invalid list, then you would know that it has been checked. Right, maybe we could continue offline about this. I think this is an interesting design here to keep the invalid list.
Yeah.
Yeah, but what I don't understand is that if one list of invalid is listed and the other one is unchecked, where is the valid list?
In the block.
Valid list is in a block, yeah.
Ah, so it's in the transaction list of a block. Okay.
Yeah.
Okay.
So the analysis is like the main thing is like when we the this is a standard model in this kind of analysis. So so when let's using like say in a way we when we consider permissioned blockchain system like such as in Hyperledger Fabric, it has some agreement and chain integrity and no splitting and almost no creation. So in this so the analysis is like in terms of the how many mistake we will make. So the it's like we consider the theorem says consider a group of collectors who are connected to the provider P, and the P offers T transactions, then the accumulated expected verification loss will be like from the governors. Let's say let this be L of T, and the SFT minimum will be like the accumulated accumulated verification loss, because just because of the better performed collectors, then we have like the difference will be like O square root here. It's like this is the best performed collector in terms of offline. Like we look it back how many mistakes we have made, and the LT is like according to our algorithm. So so if there is like a honest collector, the total number of invalid transactions will be bounded by order of square root of n. This is like just a standard approach, and let me see. Yeah.
May I ask another question?
Right.
So for the first theorem, you're saying the best behaved collector. Is that, when you say best behaved, is that based on the reputation?
It's like, can you say that again? Just one moment.
I wonder whether the best behaved is defined by the reputation.
It's by fact. It's not necessarily by reputation.
I see. So the best behaving is a grand truth.
Right. Let me see. It's afterward when we look it back. But it can make mistakes in some. But we choose the one which has like an overall minimum cost.
And in your model, even the honest collector could make honest mistakes.
Right.
Is that right?
Right. Yeah.
Thanks.
So in this case, we may have a case then valid transaction will be repeated uploaded if T is not verified, then like this number of repeated will be bounded by the number of let me see. I'm a little bit confused here. So definitely here is like for the number of connectors, they will like eventually make the right thing, and the governor will like eventually pass it. So this is like a bound on the number of repeat mistake we make here. So for incentives, it's like incentive analysis here is based on like how much they eventually gain by being lazy, and how much they cost more by getting mistakes, and with reduced reputation. So if provider contribute T transactions, then when we look at the connectors revenue, so it will be proportional to the number of times they choose in the whole process. So if they are choosing they'll be choosing in proportional to the probability e to the power of the ranks. So the higher they have the higher they have the reputation, the more probability they'll be choosing to do that to create a block. They will get more reward. So this reward they get will be proportional to the reputation to the power of e to the power of reputation. So in this sense, we conclude like this reputation they gain will help them to gain more in terms of revenue there. So so this is like the overall like structure of this construction, and the application we can talk about, like say data connection, Internet of Things. So we can also talk about other things such as human oracle, and when we have true expert to decide for the true expert to decide choosing a correct answer, or they make a mistake. That will be like the same thing with like eventually the person with higher reputation will gain more and more in terms of their reputation gain. So when we have like the rank increase, and the probability they choose increase geometrically, like in this way we can have like this the total time, like the most correct like a connector, and they would like they would like choose. So this is just one application we posted here, but it can be applied, say, human oracle design, those kind of things. So this is the overall structure of this analysis. Yeah.
Thanks.
Sounds good, Xiaotie. I have a question which I didn't understand. In the slide in which you say whether a provider wants to see if his transaction was unchecked and presented again. Could you go to the transaction, to the slide, please?
Yeah.
No, when there is the extraction of the block with a Merkle tree. No.
Which is the next? Or the statement of theorem 1?
No, yeah, this one.
Here?
Oh, yeah, this one here. So the block contains S, which is the block S is the serial number.
Yeah, serial number, right.
G is the identity of the leader, whoever made the block, right?
Right. Yeah, it's the leader chosen by their rank.
Right. So then there is a list of transactions that are considered valid and part of the block, right?
Right.
Okay. Then MT is a Merkle tree. So what you're saying is that how can I, as a provider, once I receive the block, figure out whether I presented only one transaction has been checked or not? Because how do I know that the leader was presented this transaction? Because I don't see the unchecked list in the clear. I only see the Merkle tree. So if I know the other unchecked transaction, I can verify whether mine is there or not. But maybe if it is in some fixed order. But because I don't see the rest, how can I check whether mine has been checked? Or even the collector did not even send it to the provider.
Yeah, I think this TX list is are those checked ones, right? So MT contains the invalid and the unchecked list together. So
no, I think the question is
so you mean invalid ones?
Right. Since MT is only the root, is not the entire tree. Without seeing the entire tree, given the root, I still do not know whether my transaction is in the invalid list or the check list.
Right. Let me just make sure this notation I made it correctly. It's from here. Let me just make sure my notation are correct here. So TX are the TX are labeled, transaction are labeled, and collector I signed his name on that. And so block are the serial number and the need in the current round, and those are verified, right? So the notation are, oh, I see. Okay. So the question is like this part where it's like we only see the root, but we didn't see other things. So so those parts are trusted, right? Because we verified it, they are correct. But those parts, the rest are not checked, or they are checked, they are invalid.
Yes.
So this also goes back. It's like the receiver, the provider will say those are checked. So he's clear about those part. But this part in those part are hidden and empty. He doesn't know.
Yes.
So those part does not need to be considered in the analysis. That means but that only happens with a small probability.
No, what I was saying is that with this notation of slide 11, then I don't understand in slide 20, how do I know that I should recirculate my transaction? Because I have no way to figure out if it was checked or not.
Oh, yeah, if it's in the first part, the TX list, it knows it's checked, it's correct, right?
Yes.
So, but for MT, it's a small portion of it, because or when they let's see, the leader.
Seems you're not really using the content in MT.
Right. We only need to,
validate.
if we check it correctly, check the probability, we only need to check this part, right? So for those parts we are not clear, we may assume they are all wrong, even they are all wrong. The probability analysis still hold with the use of the reputation.
No, the probability analysis is okay, but I don't understand is the last bullet of the slide 20. Because upon receiving the block, I don't know how, I don't see it.
What they do is to look at the real TX list, which is
TX list, they consider those are checked.
These are all
we don't know if they are checked
valid,
or not.
invalid, checked, unchecked.
Yeah. Sylvia, you are right. Yes, this is not clearly written. So the idea is that provider take like a worst case view. So he thinks those are checked, they are correct. For those, maybe it's kind of mixed, but they put all those into unchecked list. They say that all they may want to send, they are not checked. So they may assume those are all bad. So invalid, unchecked, they are all bad. So this is a way when we say. So this statement is not right. So we need to revise it to say those are checked. They are means those parts are checked. So for those parts, some are unchecked, some are checked, but invalid, we rewrite them as none of them are checked.
Okay.
That's the idea. So we didn't put it right. Like literally it's wrong, but the idea behind it is like
yeah. I understand. Okay, thanks, Xiaotie. Great. Sounds good.
Thank you.
Thank you. Great to have you.
Xiaotie, actually, what I like is that this. So your analysis is a little bit more general, seems to me, than blockchain, right? I mean,
right. We also use it's like a technique from other area, like
Yeah, you can apply it to a lot of stuff.
Right. Yeah, like we also use it to study human oracle design. Use this.
Yes. For instance, yes.
Yeah.
And because in fact, actually, for human Oracle, they can be even more expensive to check. And therefore, you want to save checking, right? Because after all, a transaction, you can check it quickly by computer if you can keep the history. But when you want to go out in the world and figure out an Oracle, that is very slow. And so that the same technique you say can apply there. Yes, okay, yes, I agree. It's very, very nice. Thanks.
Yeah. Thanks a lot. Yeah.